and welcome to Bay College's Intermediate Algebra online lectures. This is section 6.2. We're going to deal with rational exponents. And what rational exponents means, rational numbers can sometimes be fractions. Well, now we're going to look at cases where exponents can sometimes be fractions. One example is a to the 1 over n, where n is just some number, we have a fraction. We can rewrite this to a radical, just like we seen in the previous section. The nth root of a to the first power. Essentially, if we look at this, when we have a fractional exponent, the denominator of this fraction is n. That is the number of our index. And the numerator is the power of the base. So we have a to the first nth root. Well, that's the same as a to the 1 over n. And obviously n has to be greater than 1 because we can't have a first root. That doesn't really make sense. So n would be like 2 or 3 or 4 or some integer. So essentially what we're looking at is if we have something like the square root of 49, we can write it as 49 to the 1/2 because a square root is a 2 in the denominator of a rational exponent. Now, we could take this further because sometimes writing from a radical to an exponential form can help us simplify our radicals. And one example here is, well, let's just break down 49. What is 49? Well, it's 7 squared. That's the same thing as 49. What are we doing to 49? We're raising it to the 1/2 power. Now, it's very essential to understand your rules of exponents when dealing with rational exponents because it still follows those same rules. So if you're a little rusty with those rules, definitely brush up. We'll actually review some of the rules in this section. But you should be very familiar with your rules of exponents. It will help you tremendously. As an example, looking at this, now that I've written it this way, I can simplify this by using my power rule of exponents. When I have a power raised to a power, I can multiply them. Well, what is 1/2 of 2? Well, 1/2 of 2 is 1. 7 to the first power is 7. So by writing it as a rational exponent and then simplifying, we can come to the same answer. Now, some of you intuitively look at this and say, well, the square root of 49 is 7. Well, 2 times 1/2 is 1. We get 7 to the first power, or just 7. We get the same result. But sometimes when we're dealing with larger polynomials or other expressions with many variables, sometimes writing it in this form is actually going to help us come to the solution. Let's look at another example here. Here we have the 4th root of 1/16, which can be written as 1/16 to the 1/4 power. Well, let's split this up here into its factors. 1 is 1. Only factor is 1. 16, if I break it all the way down doing a prime factorization, I get 2 to the 4th. That's the same thing as 16. Now it's raised to the 1/4 power. Well, as we discussed in the previous section, 1 to any power is still 1. So the 4th root of 1, or 1 to the 4th power, is equal to 1. And essentially we're applying our quotient, or our power of a quotient rule here. We distribute this to each of the powers. Well, 1/4 of 4 is just 1. So 2 to the 4th raised to the 1/4 power is just 2. Essentially multiply 1/4 by 4. And we get 1. So we simplified the 4th root of 1/16, writing it as a rational exponent and then factoring what we have here. It breaks down to 1/2. The other way to do it is, if you recall in the previous section, we used the quotient rule of radicals. The 4th root of 1, the top number, is 1. The 4th root of 16 is 2, the bottom number. And we get 1 over 2, the same result. All right, well, let's look at this. Here we have 16 to the 3/4 power. Well, how can we deal with this? Well, we can break it up a little bit. We can say, well, this 3 is the power of 16, and this 4 is the index of the radical. So let's go the other way. Instead of taking a radical and writing it as an exponent, let's take an exponent and write it as a radical. Here I can say, well, this is the 4th root, my denominator indicates my index, of 16 to the 3rd power. Now I can write it this way, or I can write it this way, the fourth root of 16 raised to the third power. These are actually all equivalent, okay? Because multiplying by 3 or dividing by 4, these multiplication and division can be done in either order because they are essentially reciprocal operations. So if we look at this, we can say, well, the fourth root of 16 cubed, well, I can cube 16 and get a huge number and then take the fourth root of it. But if we look at this method here, well, the fourth root of 16 is 2, as we've seen in this example, and 2 cubed is 8. This is my preferred method because if we can take roots before we apply powers, we're going to actually deal with smaller numbers because roots give us smaller numbers. So if we simplify this, the fourth root of 16 is 2, and 2 cubed is 8. So 16 to the 3/4 power is 8. All right, so what is this property that we're actually using in that last example? Well, that's this here. If we have some base to a fractional exponent, we can write it in one of two ways. We can say the denominator is our index, and that numerator is our power of that base. Well, we can write it this way, or we can write it this way, because essentially multiplication or division can be done in any order. Let me just rewrite this for a moment. We can say this is a to the 1 over n raised to the power of m, because if I multiply 1 over n times m, I get n over m. Or I can write it as a to the m raised to the 1 over n. So that's essentially what we're saying. We can write fractions as radicals. Fractions as radicals and vice versa. So radicals are nothing more than fractional exponents. So let's take a look at this. This here is my preferred method because if I take a root before I raise it to a power, I'm going to deal with smaller numbers, more manageable numbers. So that's what I'm going to do here. I'm going to say, well, the denominator of this fractional exponent, 4 to the 3/2, is 2, so I'm going to take a square root of 4. But my power is 3, so I put the power up here. So the square root of 4, well, we recognize that to be 2, and 2 cubed is 8, so 2 cubed is 8. So we could do the radical before the power, and sometimes that'll give us a smaller number, more manageable number that we can then work with. If we look at this, we have 8 to the 5/3. So I'm just going to rewrite this as the cubed root of 8 to the 5th power. Now I could raise 8 to the 5th power first, but that's going to give me a huge number, and sometimes we don't recognize those factors when we deal with larger numbers. So the cubed root of 8 is 2 to the 5th, and 2 to the 5th is 32. 2 times 2 times 2 times 2 times 2 is 32. All right, let's look at another property of exponents, and that's a negative exponent. It's called our reciprocal. Well, when we have a negative exponent, we can rewrite it as 1 over that base to that positive value of exponent. And of course, our base cannot be 0, because that would make this undefined. We can never divide by 0. And again, n is greater than 1. Our index starts at 2, essentially. If we look at this example, this is a rule of exponent. If we have a to the negative m over n, here it's just a rational number. It's now a fraction. We can rewrite it as 1 over that value. And we can take it further using this rule here. We could maybe write it as 1 over the nth root of a to the m power. And I'll just put that in here. It's really not crucial, but we'll tie them together. We're talking the nth root of a to the power of m. So these are all the same here. All right, let's look at this example. We have negative 64 raised to the negative 2/3 power. Well, first of all, let's deal with that negative exponent and take its reciprocal, 1 over negative 64 to the 2/3 power. I'll clean that up a little bit. Hopefully it's visual in the video here. So we have 1 over that. So we just got rid of that negative. Now we can apply the previous rule here, and we can rewrite this as 1 over the cubed root of negative 64 raised to the second power. Well, what is the cubed root of 64? 64 is a perfect power, and since our index is odd, it's okay to have a negative in there. So I'm going to get the cubed root of negative 64, which is negative 4. Now, what's negative 4 squared? Well, negative 4 squared, let's write that out, negative 4 after we take that cubed root. And now we can apply that power of 2. Well, negative 4 squared is 16, a positive 16. So I get 1/16. So you see we started with this negative 64th to the negative 2/3 power. We took its reciprocal, we applied our index and then our power, and we got a value of 1/16. All right, what if we have this? What if we just have a variable x to the negative 1/3? Well, this negative just tells me take its reciprocal. 1 over x to the 1/3 power. So we got rid of the negative, and now we can write this as a radical. 1 over the cubed root of x to the first power, because my numerator is 1, so we can just stop right there. Now this isn't in proper form because we have to rationalize the denominator here, but we'll actually see that in the next section, 6.3. All right, one last example that applies negative exponents, and a very important one, is we have the quantity 2 divided by 3 times y to the negative 5/7. Here's where we need to be careful. This power only applies to the y, not the 3. There would have to be parentheses here in order for all of this to be raised to the negative 5/7. Well, what happens if we have negative exponents already in a denominator? Here we brought it down to a denominator in these examples. Well, here its reciprocal just means bring it up top. So I'm going to rewrite this as 2y to the 5/7 over 3. Notice the only thing that I moved was the y to the 5/7. If I bring it up, I just change its sign. That is its reciprocal. Now, I could rewrite this as a radical, but because it's a variable, a y value, I really can't do any simplifying there. But if I did want to write it, if I were maybe instructed to change it from exponential to radical notation, I'd have the 7th root of y to the 5th over 3. These are identical, and I could even change it up a little bit, have that 5 outside of this radical as long as it's in parentheses, right? So different ways to express your answer, but this doesn't simplify any further. Just wanted to point out when you have that negative exponent and it's already in the denominator, essentially all you got to do is bring it to the numerator. Just switch it. It's reciprocal, right? All right, so let's, we've already seen some application of our rules of exponents, but I just want to stress how important it is to know your rules of exponents when dealing with radicals, because radicals are rational exponents, fractional exponents. Well, it doesn't matter if we're dealing with integers or fractions, they all follow the same rules. So radicals do follow all the rules of exponents. So if I have our power rule, or excuse me, product rule, a to the m times a to the n, we can add them. Quotient rule says I can subtract them. Our power of a product says I distribute the power to each in this being multiplied, a to the n, b to the m. Same thing with the quotient rule, power of a quotient rule. I have to apply it to the a and to the b in this example. We have the power rule is if I have a base to a power raised to a power, I multiply their powers. Don't forget the power rule. Here is the rule that we just seen in the previous example, the reciprocal rule, or the negative exponent. We just write the reciprocal. And one thing we always have to remember is any value to the 0 power is 1. All right, so let's look at some examples where we can apply those rules and the two other rules that we looked at changing these to either powers or rational exponents. Now, if we look at this, this looks very similar to that first rule of exponents, our product rule. We have the base a, the power 2/11ths, and 5/11ths. Well, we know when they have the same bases, we can just add them, right? Well, good news is they have the same denominator, because we still have to remember all those other rules of math where in order to add fractions, they have to have a common denominator, and we can see they do. So 2/11ths and 5/11ths is a total of 7/11ths. So we have a to the 7/11ths. So we were able to simplify that. And we can take it further. Maybe we want to write it as a radical. It's the 11th root of a to the 7th, or that 7 could be outside here if we put that in parentheses. Now here we have 4u squared raised to the 3/2 power. Well, what we can do here is we can think of this as our power of a product, and at the same time, our power rule, where we have something to the power being raised to the power. Essentially what we need to do is to distribute this to both of the values in here, 4 and u squared, because these are being multiplied. So we can write it as 4 to the 3/2 and u to the 2 times 3/2, which would just be 3. It's one way we can simplify this. Now, well, let's deal with this. This u to the 3rd, well, that's just some variable to the 3rd power. 4 to the 3/2. Well, we can rewrite that as the square root of 4 raised to the 3rd power u cubed. And if we simplify this, the square root of 4 is 2. 2 to the 3rd power is 8. So we get 8u cubed. Now that seems like a lot of work, but with time you'll be able to take some shortcuts with practice. So essentially if I distribute that, I'm going to say the square root of 4u squared is going to give me 2u. 2u cubed is 8u cubed. So you can take those shortcuts eventually with some practice and be able to jump right to that. All right, here, well, we already have it in a radical form. Let's rewrite it in an exponential form and use our rules of exponents to maybe simplify it. Essentially, I have 3 to the 2n power. That is my numerator of my fraction, and the index is my denominator. So I have 3 raised to the 2n over n. Well, if we notice here, an n in the numerator and n in the denominator of our power, we can actually reduce that. N over n is 1, so I end up with 3 squared. Essentially, this reduces to 1. So 3 squared is 9. So this didn't look very nice, and we had n in our index. We didn't even know what our index was, but by simplifying it, we came to a nice integer number like 9. Well, what about this? The 4th root of 36. Well, let's stop for a moment and say, what is 36? Well, 36 is 6 squared. And now we can simplify that and say, well, let's write this as an exponent now. I have 6 to the power of 2, index of 4, 2/4. Well, what we recall about our fractions is we should always reduce them. Now, if you remember in the previous video, one of our rules of simplifying radical expressions is to have the index as small as possible. Well, we can see by writing it as a power here, 2/4 actually reduces. So we end up with 6 to the 1/2. 2/4 is 1/2, so these are equivalent. And now, notice my index is 2. It is as small as possible. If I rewrite it, I have the square root of 6. So the 4th root of 36 and the square root of 6 are actually the same value. This one has a smaller index, and the radicand is also smaller. So we've simplified it using our rules of exponents. All right, and lastly, we have the 9th root of y to the 6th, z to the 3rd. Let's use our rules of exponents here and say, well, this is the same as y to the 6th, z to the 3rd, all raised to the 1/9 power, because this just says it's denominator, right? My index is the denominator of my power, 1/9. And now we can use our power rule and distribute this 1/9. Y to the 6th over 9, z to the 3 over 9, just by distributing that using our power of a product. And now we can simplify it. Well, what is 6 over 9? Well, that's 2/3. Y to the 2/3 power. And z to the 3/9 power would be z to the 1/3 power. And now we notice, well, hey, we both have denominators of 3, so my index is 3. I can say the cubed root of y squared, my power, z to the first, which would just be z. And we can see cubed root of y squared z. Notice we decrease the index from 9 to 3 using our rules of exponents, and also decreased our powers. And does this meet all of our requirements that we've seen in the last video? Our powers are less than our index, and the ratio of our index and our powers are as simplified as possible. So this here is the most simplified radical expression. This has been section 6.2. Keep practicing. Thank you for watching.